Okay, good evening, ladies and gentlemen. This is the masterclass, and we're going to be looking specifically at the Doppler effect. All right, so let me quickly share my screen so that you can see, oh, not that screen, that screen. There we go. All right, so let's make this a little bit bigger so you can see it. I thought we'd start off with a multiple choice question, which should be really obvious to most of you, but I just thought it was a nice kind of groundbreaker because we didn't look at too many of the applications when it came to the Doppler effect. So I'm going to quickly pause and give you a chance to select your right answer. So question 1.6 says the Doppler effect is used in medicine to, please have a look and pick the answer that you think is correct. Okay, good. Okay, fantastic. So I haven't even written anything down, but we'll do it anyway. It's not used to detect cancer, okay? You can use gamma radiation to treat cancer, but that's not what we're asking. It's not used to determine the length of an artery. It can be used to monitor the heartbeat of a fetus, but not to monitor the growth rate of a fetus. So it's technically to measure the flow rate of blood, either through the human body or in this case, the fetal heartbeat. All right. I hope that everybody got C. Can I quickly just have a show of hands who got C? Okay, good, good, good. Okay, fantastic. That looks like everybody, so you guys do know what you're doing. Fantastic. All right, let's quickly clear these. Move on to the next question. All right. Oh, where did it go? There we go. Okay, so I may have to scroll out just a little bit to make sure that we can see this question clearly, because I want us to be able to answer it. Okay, that's a little bit small, but can everybody read that? Let's make it so that I can check. Okay, you can all read it. I did start to wonder the other day if anybody's reading these on a cell phone, it could be really uncomfortable. I'm sorry if you're ever reading this on a cell phone. I'm hoping it's not the case because the font does get very small. All right, okay. So let's have a look over here. A police car is moving at a constant velocity with its siren on. If it's a siren on, this means that the police car is the source. And it passes a stationary listener, which means we've got a stationary observer. So the observer has a velocity of 0. It's very important as you're reading through the information that you immediately identify what's the source, what's the observer, and which of the two is going to be stationary. Please note they'll only ever have one moving and one stationary, so you've got to try and identify which one's stationary. The graph below shows the changes in the frequency of the sound of the siren detected by the listener. So you'll see that it goes from 170 down to 130. We know that the higher frequency will be when it is moving towards, and the lower frequency when it is moving away. I hope you remember that. Okay. 6.1 is a very commonly asked question because it is, I guess, the only real definition that we can ask here. So I'm going to ask you all right now to please state the Doppler effect in words. Okay, and then to write down the frequency of the sound detected by the listener as the police car approaches and as it moves away. These should be very, very quick. So I'm going to ask you to do it as fast as you can, just those two. Okay, go for it. Okay, please give me a thumbs up when you've got to that point. Okay, fantastic. All right, let's resume and go through this. So the definition of the Doppler effect is that it is the apparent change in frequency of a wave due to the relative motion of the source and the observer. The key words are the apparent change in frequency and relative motion of source and observer. Those are key concepts that you've got to have there. The frequency of the sound as the police car approaches the listener is 170 hertz, and as it moves away is 130 hertz. Just something to note, sometimes this may be, and we don't usually do it with sound, but it might be kilohertz if we're dealing with a different range of frequencies or something like that. So just always check that you don't have any weird things down the side here that say times 10 to the power of 6 or other nonsense, or you're really going to mess up badly. All right, now that we've established this, and I've got the formulas written at the top over there, the question says, calculate the speed of the police car. So we're working out VS, that is the question. That's what we're looking for, and you're asked to take the speed of the sound in air, which is just our normal value of V, is 340 meters per second. Now, I'm warning you already, this is going to be a simultaneous equation. So my advice is to set up a separate equation using the 170 hertz for when it's moving towards and the 130 hertz for when it's moving away. And once you've set up those two equations, you're then going to have two unknowns. You're going to have the velocity of the source, and I think you're going to have the actual frequency. Yeah, the actual frequency, the true frequency of the source is also going to be missing. And from there, you're going to do a simultaneous equation and only solve for the one. All right, I'm going to pause now, and I'm going to give you a little bit of time to do this. Please, when you get to the answer, just give me a thumbs up. But I suspect that I may get there, and then I'll be able to check out when we get to that point. Okay, go for it. Okay, has everybody got their first two equations set up at this point? Find that it's a good place for us to check in before we end up racing off and doing a simultaneous equation with the wrong equations. All right, so let me just quickly share. Okay, those are the two equations I've got. Please remember, if they're moving towards each other, the frequency goes up. So this must go up. In order for that to go up, the denominator must be smaller. Same number divided by a smaller number means everybody gets more. So that was the one relationship, and then the other was the 130 is that way around. Please, just a little note for you. Remember, we are trying to solve for VS. So it makes life easier if you make both of them become FS and then equate them. But I'm not going to tell you how to do simultaneous equations. That's just a hint. Okay, go for it. Wow, someone's fast. Okay, good. This looks like it's a very, very naughty police car. If you quickly work out how fast he's traveling in kilometers per hour, you will see he's going way too fast for being legal. All right, can I quickly just ask if you're already done? I know some of you have already given me a thumbs up, but just quickly do it again so that I can double check who I'm still waiting for, if anybody. Okay. I think there was just one person, so I'm going to continue now. All right. It should be long enough. All right, so what I did here to get FS on its own was I multiplied this value up to the top and that 340 down to the bottom, and I did it on both sides. So when I cross multiplied, I ended up with 170 times by that value divided by that value equals 130 times that value divided by that value. The 340s were good and nice and neat, and they both canceled out. And then I slowly multiplied in, so I did distributive law there and there. Get good with your maths. It's terrible when you lose marks for maths and science. And from there, I then took all of my variables to the one side and my constants to the other. And I got a value of 45.33 meters per second, which I think ended up being somewhere around about 160 kilometers an hour. Can I ask, is there someone telling me I made a mistake? Or where do we get marks for working? Oi, okay, I'm making this up as I go. 1 mark for the formula, 1 mark for equation 1, 1 mark for equation 2, 1 mark for equating them, 1 mark for the answer. Okay, pretty sure that that's right. So usually it's 1 mark for each equation, 1 mark when we equate, 1 mark for the answer with units. Please, can I give you a little bit of advice? Always check that your answer makes sense. You'll notice that I got to the end and I got an answer in meters per second, and my first instinct was to turn it into kilometers per hour. The reason for that is that my brain doesn't compute what 45 meters per second is. I look at it and I'm like, ooh, that's, and then I don't even know whether to say super fast or super slow. I know it's faster than a person can run, but I don't know if it's that fast, or, I mean, somewhere in my head, there's a little random fact that says that 20 meters per second is 72 kilometers per hour. So it's faster than 72 kilometers an hour. But I always find that I check it, because if this police car had suddenly been going at 1,000 kilometers an hour, I should be doubting it. Okay, that's faster than an airplane. So it's a very good idea to always just check that your answers fit in within the logic of what knowledge you have. Okay. All right. Is everybody happy with this question? Did it make good sense? Was there anybody who didn't understand how to do the simultaneous aspect of it? Please, one other thing, we weren't actually asked to work out the frequency here of the source, but you cannot, and we have mentioned this before, you cannot assume that the frequency was 150. It's very tempting to go, oh, it's halfway between the minimum and the maximum, the coming towards and the going. It doesn't work that way. In fact, I'm going to ask just quickly, because I don't have lots of questions for us to do today. I'm going to ask everybody to quickly calculate on this same question the frequency of the source. I don't know if any of you did it en route. If you did, that's fine. You can just quickly use your value. If you didn't, I'm going to quickly be calculating mine as well. All right, you should be able to use either of the values with what you've already done. Shh. All right, good. I can see one person's got it. Has everybody else got it? And what you'll notice very quickly is it's close to 150, but it's not 150. And if you used it, you wouldn't get your marks. Okay, so I randomly chose to take this top equation and to sub it in there to get it. But it's just to point out to you that there is alternatives. So some of you may not ahead of time have worked out that you needed to equate your two FS values to be able to solve for VS. Some of you may not have worked that out. You may have solved for FS and then had to go back and work out VS. That's perfectly acceptable. You aren't going to get penalized for doing extra work if you still get to the same answer. All right, everybody happy with that question? Well, good. Let's quickly clear it and move on to the next question. Okay, I'm going to make you repeat the same questions again because it's so important with the Doppler effect that we do know our definition. So this question here says a racing car approaches the finishing line in a race at a constant speed of that value. The engine of the car produces sound of frequency 1,200 hertz, and the speed of sound in air is 340 meters per second. You are asked firstly to state the Doppler effect in words. I'm going to ask you to humor me and write it down, even if you've written it down earlier on the page. Turn over new page, do it again. Then I want you to work out the frequency of the sound heard by a man standing at the finishing line. And lastly, to draw a graph of frequency versus time for the sound as the car approaches the man and then passes him. All right, so I'm going to quickly pause this and ask you to get started on all three of those questions. Good luck. Okay, is everybody coping? Good. Wow, that was fast. Okay. You guys are all beating me. I've been just quickly looking for another question, so I'm far behind here. All right, we may in fact just work through this one together so that I'm not racing to chase up to catch up with everybody else. So let's quickly have a look at this. The first question says, state the Doppler effect in words. It is the apparent change in frequency of a wave due to the relative motion between the source and an observer. The next question says, calculate the frequency of the sound heard by a man standing at the finishing line. So since he is approaching, they're moving towards each other, which means that the frequency will go up. So if we use the equation that FL is V plus or minus VL over V plus or minus Vs times Fs, please, I recommend here fully that you show the formula each time. Okay, so here what I need to do is I need to establish here that the man is standing, so the listener is stationary, so it's V over V Vs, approaching, so it's got to be minus times by Fs. So we know that the engine is what's producing the sound, so the source has that velocity. Okay, so we're looking for the frequency that the listener heard. We know we can use 340, so it'll be 340 minus, now these are very close values, so I often find that if the speed of the car or object is approaching or getting closer to the speed of sound, then the frequency changes a lot. Frequency of the source is 1200, and if I work that out, it's 340 divided by 340 minus 284.4 times 1200. Did I do something wrong here? I get a very big value, 7338.13. Okay, let me just quickly check. Oh, yes, thank you. I didn't pick it up. Kilometers per hour. Thank you. I was doing this too quickly. So yes, we've got to turn our kilometers per hour. I was thinking it was a bit huge. I think I've made that same mistake before recently. So 284.4 divided by 3.6 to convert kilometers per hour to meters per second. You guys are on the ball tonight. Gives me an answer of 79.03 kilometers per hour. So here it's going to be 79.03. I do usually find that if they're very close, I do wonder. And I must admit, there was a tiny part of me that was going, wow, that's really fast for a car. But I guess if it's a racing car, we can overlook things if we don't know exactly how fast they travel. So 340, thank you, divided by 340 minus 79.03 times 1200 gives me an answer of 1563.398. So I'm going to make it 40, and that'll be hertz. Okay. Having got that right, second time round, can I ask who got the same answer? Did I make a mistake again? I don't think so. Okay, good. So some of you did. You're then asked to draw a frequency versus time graph for the man. Now, what was nice about this question is that we'd actually done something similar in one of the previous questions that we did this evening. So the important thing here is you must label your axes. It's frequency in hertz against time in seconds. You've got to have all of that. Okay, so initially we're going to have a frequency that is above. Now, I don't know, please just with this, I know I always draw the line up and down. Please, we never go to negative frequency. So it should be frequency here to frequency there. Okay, so please make sure that you haven't done above and below the line. This is probably 1563. The true value is somewhere about 1200. And if this is about, I don't know, 350 above, this will be somewhere around about 900-ish. Okay, very-ish. But you can see that both of them will be above 0. Who got that diagram correct? Okay, fantastic. Is the drop at a 90-degree angle? It doesn't really matter. If you do a curvy drop, you're effectively saying that the change in frequency takes place over a range of time. As far as I'm concerned, it takes place as you pass. So I don't mind if you do it as a straight 90 or if you do it a little bit over time. I must be honest, I think I prefer the straight 90, although it probably isn't that realistic in terms of how quickly your ear may hear the change. I'm not actually certain, but I'd say here that isn't what they're checking. They're checking you've got a constant value that then goes down to another constant. Please don't make it curve over a really long change like that, because that's technically saying that the frequency changes gradually and the frequency doesn't. I'd actually go very clearly. It's an instantaneous change as far as we teach you. All right. If you think about it, you also don't learn that there's a difference as it gets closer. There may be a difference in the loudness. Okay. All right, so I've got another question saying, ma'am, in some of the prelim pass papers in Siyavula, they deal with the Doppler effect underwater. Why is the speed of a wave slower in water than in air? It's actually faster, usually, the speed of a wave. So I usually work with the speed of sound specifically. Sound through air is usually about 330, 340 meters per second. Whereas through water, it's usually about 1,500. I remember years ago, I caught is the operative word, I caught my children. And my eldest son was doing science homework. I think it actually was legitimate science homework, where he had my youngest son on the other side of a table. Both of them had their ears pressed, or one of them had their ears pressed against the table, and the other one was hitting the table, and they had to measure how long it took for the one to hear the sound that the other had made somewhere. And they were actually doing experiments on how fast sound traveled. Now, sound travels a lot faster underwater than it does through air, because the particles underwater are closer together. And if you remember, sound is a longitudinal wave, so it actually needs the particles, the medium, to move apart and to move together. So the closer the particles are, the better the sound transmits. So I don't know if I'm going quite with what your question said, because it seems, I think what you'd written was the opposite, but let's just quickly check here. Okay, good. All right. So you did gravity is faster. It's just that sound travels faster when the particles are closer together. In fact, sound travels even faster through a solid. Okay, but you've got to remember that this is specifically sound, not light. Light will, on the other hand, slow down as the medium becomes more dense, because it's an electromagnetic wave, and having a medium there actually doesn't work to its favor. Mediums slow it down. So if you're making it travel through air, it slows down more than it would through a vacuum, etc. Whereas sound waves need a medium. So the more dense your medium is, the better they travel. That's one of the reasons why if you stand outside a swimming pool and you listen to that tick, tick, tick that a creepy crawly may make in a swimming pool, you can't hear it usually that clearly outside. You go underwater and the sound travels brilliantly. Okay, you can hear it. It's in fact very loud. Okay. All right. Is everybody good with this question? I think when it comes to the pedantics of whether we drop a vertical or not, I'd say it's safer to drop a vertical, or if you don't do a vertical, make it a steep thing, make it look so that it's like a vertical where your ruler didn't go vertical, but just tilted slightly to the side. So make it the kind of vertical where somebody has to think really hard about whether it's vertical or not. All right, let's clear this and move on to the last question for today. We may actually put in another one after that, we'll see. But I'd rather we had time to do things properly. You'll notice that the Doppler questions generally aren't the most generous in terms of marks. All of the questions that we've looked at today have been between 9 and 11 marks. So it's a quick section in your exam, but as always, it's quite a lot. 10 out of 150, 6%. That means that it's about 3% once you bring in your chemistry as well. And that 3% can make quite a big difference if you're scoring all of the marks. I think you can rationalize almost every section in this matter. In the same way. Okay, so the next question says, a police car is moving at a constant speed on a horizontal road. The siren of the car emits a constant frequency. Each of two observers, A and B, standing some distance apart on the same side of the road, records the frequency of the detected sound. Observer A gets 690 hertz, and observer B gets 610 hertz. Please note the police car is traveling, but I'm not yet going to commit to which way is traveling because I don't want to give you the answer. So question 6.1, and I'm going to ask you to write it one more time, is to state the Doppler effect in words. 6.2 In which direction is the car moving? Is he moving towards A or away from A? Please be smart in an exam. Don't just say toward, well, I guess you could say towards or away, but make sure that you're referring to A. Don't refer to B. Towards or away from B, that wasn't the question, and give a reason. And then your next question with the multiple choice, no, sorry, not multiple choice, with the simultaneous equation is to determine the speed of the police car and to take the speed of sound in air as 340 meters per second. Now, this is almost identical to the one where we were given the graph and we read off the two frequencies. So them giving you a graph made it harder because a lot of people really struggle with graphing skills, but it's not actually that different as a question. And then lastly over here, name one application of the Doppler effect. All right, I'm going to ask everybody at this point, I'm going to pause it and I'm going to ask you to do all of those in one go, and then we will compare answers in just a second. All right, go for it. Did one almost identical to this. This is really good practice for you to figure out if you know exactly what's going on. Those are very big numbers. Okay, has anybody got an answer yet? Okay, if you have, can I ask you to just please write it up in the chat so that I can double check against mine? If you're brave. Okay. Good. Okay. Just going to give everybody else a second longer. go through it in just a second. I'm just quickly scrounging for a last paper to do today because you guys are motoring through these. Going faster than I'm ready for. Ah, there we go. That's a good one. All right, so let's quickly reveal and go through this. I think everybody has got the same answer, which is fantastic. Well done. Okay, so if I resume my share over here, I got stating the Doppler effect. The Doppler effect is the apparent change in frequency due to the relative motion of a source and an observer. The car is moving towards A because A has a higher frequency. To determine the speed of the car, we've done one almost identical to this earlier on. So it was just plugging in the values, making sure if you had the higher frequency that you subtracted Vs, so moving towards, and if you had the lower frequency that you added Vs. Then doing an equating, and then lastly solving to get the answer on its own. Because you were asked for speed, you didn't have to put in a direction. Okay. And then lastly, name one application of the Doppler effect. I'd say to measure the rate of blood flow or to measure and detect fetal heart rates. Did anybody else put in any other uses of Doppler effect? You can use it to measure the speed at which cars are traveling. So therefore in speed trapping and things like that. All right. Can I just quickly ask before I move on to the last question, because I'm going to be jumping across to an actual exam paper, can everybody make sure that they've got this equation written down? Because I'm going to have to take a second to quickly cut and paste it into here once I've shown it to you. All right. Everybody got that? Can we move on? Last question for today. Okay, so let's clear all drawings. Here's the question. Oh gosh, which one was it? Okay, this is the one I made to go to. Yay. All right. So I'm going to do this. This one's coming directly from an exam paper now, but I'll cut and paste it into my Word document just now. So it says, the alarm of a vehicle parked next to a straight horizontal road goes off, emitting sound with a wavelength of 0.34 meters. A patrol car is passing, moving at a constant speed on the same road, and the driver of the patrol car hears a sound that is a frequency of 50 hertz lower than the sound emitted by the alarm. Take the speed of sound in air as 340 meters per second, and you're going to get started with this. I am hoping that I haven't already done this question with you. As I'm reading it, I'm suddenly wondering if I have. Do you know what? You can always double up. I'm going to quickly check. Maybe I'll stand corrected just now and go, it's the same one. All right. So can I pause while everyone quickly checks that? And I'm going to go back through my Doppler notes and check that I haven't given you this exact same question before. I think sometimes as teachers, we have so many of the same questions that we start to have deja vu and we don't know whether we've seen it here or where we've seen that particular question. All right, I'm just quickly checking through the ones that I've got from my previous notes, and it looks like we haven't done this exact one. Yay! All right, cool. So this isn't one that you'd have done with me, at least in the last little while. Okay, brilliant. So can everybody quickly get started on that? I'm going to cut and move it across and then start answering it as well. There we go. I've got it all set up so we can see it again. Yay. All right. Sorry about that. Sometimes I prep these really well, but I've had 2 sessions back to back tonight, and I just underestimated how fast you guys would work. Okay. Please note, I haven't given the equation V is equal to F lambda. I presume you remember it, but you need to know that if they ever give you wavelength, you've got to be able to work between the two. You've also got to think very hard in this question. What's the source and what's the observer? Good. I hope you're all doing both of the questions that are still left there. So not just 6.3, but 6.3 and 6.4. 6.3 was nice and easy. Yep, good. Okay, I'm happy with the frequency of sound that they've posted. That is correct. And I'm happy with the distance traveled. Well done. All right. Are we still waiting for anybody else who hasn't yet got to the answer? Okay, I'm going to then share. All right. So in this particular case, as always, the Doppler effect is the apparent change in frequency due to the relative motion of a source and an observer. Because the frequency is lower, we know that it is moving away. There is a relative motion apart from the parked vehicle. You were asked to work out the frequency of the sound emitted by the alarm, so you use the equation V is equal to F lambda. Please note here, our V is 340. That is the speed of the sound in the medium. So you've got to make sure that you use that V. I can understand how there's so many velocities getting thrown around that you sometimes forget, but it's the actual wave speed, how fast that wave is traveling through its medium, in this case, the speed of sound in air. The wavelength was 0.34, so it gave us a frequency of 1,000 hertz. We then had to rearrange our equation. Now, as always, I recommend you write down the exact one written on your data sheet. Don't bother trying to rearrange it just in case you do it wrong. Okay, we don't want that. So the bit that may have been tricky was working out how to get the 50 hertz lower. So if its true frequency is 1,000, you've worked it out there. This frequency is 50 lower. The other thing that was tricky and nasty in this question was that the source was parked and the police car or patrol car was moving. I think what sometimes happens with a question like this is that people assume that the alarm is coming from the emergency vehicle. They read patrol car and they decide that the alarm is on the patrol car. It's one of those weird things that if they had just told you another car was moving instead of it being a patrol car, you probably wouldn't have made that error. But a lot of people here would get very confused about the fact that the velocity of the source was 0 and it was the observer that was moving. Just be very cautious of that because it's a common mistake that people make. So you then plug everything in and you get an answer of 17 meters per second. What you then have to do is go back to what we were told, that he drives at a constant speed. I don't encourage my students to use this formula very often because the problem is that a lot of people use it when there's an acceleration and then it doesn't work. So this equation is only for constant velocity. And if you use it at any other time when there's acceleration, it doesn't work. So you've got to make sure that you've got this constant velocity to begin with, or there's a big problem. So we then go in by plugging in our constant velocity, it shouldn't be a negative, constant velocity of 17. We're looking for the distance that it covers in 10 seconds, and we get that it covers 170 meters. All right. Okay. I'm going to just quickly ask you if you want to take any photos or a few screenshots, there's the word, please do so quickly. All right, I hope that made good sense to you. Okay.